Hello, everyone, and welcome to the summit. I'm Christian Schroeder, Vice President of Systems Engineering for Yellowbrick. I lead a team of global systems engineers that work with our customers to solve some of the largest problems in data warehousing. In our talk today, I'll be covering the Yellowbrick Architecture 101 session, which explores technology concepts that separate Yellowbrick from the competition. Now let's jump right into the session. To get started, I wanted to talk a little bit about what Yellowbrick is. For those of you that aren't familiar with us, we've created a SQL database designed for data warehousing and ad hoc workloads. Yellowbrick is a massively parallel, or MPP database designed for processing SQL queries across many nodes in a cluster. Our differentiation is our real-time results on the most demanding workloads. We're designed to run efficiently against very large data sets, providing guaranteed response times. This is the same efficiency that allows Yellowbrick to provide real-time results, even with small edge-based deployments. Today, I'm going to talk about the origins of legacy data warehousing architectures and the challenges that come along with those. I'll talk a little bit about Yellowbrick innovations, the Yellowbrick architecture and how that applies to distributed cloud. We'll get into our replication capability. We'll also talk about how we approach security, and we'll get into a conclusion. But before I get started on any of that, one of the questions I usually get when I'm talking to a new customer is what makes Yellowbrick different? Why does the world need another data warehouse? And to answer that question, I usually find it useful to talk about what technology was available at the time when most of these data warehouses were written. About 15 years ago, or sometimes even further back than that, is when most data warehouses were written. And if you take a look at kind of the technology that was available at the time, you'll find that the most common way to store data in primary storage was on disk drives. Solid state was around, but wasn't really at any kind of usable scale. And traditional disk drives are kind of the equivalent of a record player spinning. And they only provided about 100 megabytes a second of bandwidth per device. The most common networking was 1 gigabyte networking, and top tier CPUs only had about 2 cores at the time. In DRAM, I think the largest module was somewhere around 2 gigabytes. And at this point in time, VMware had just IPO'd and there was no cloud. If you take these constraints into consideration at the time when people were designing data warehouse software and technology, you quickly come to a conclusion that you have to keep most of the hot data in memory to achieve reasonable performance. All that hot data has to live in a cache or your performance is going to suffer because you can't reach out to those slow disk drives. DBAs were required to create and manage large indexes to achieve any kind of decent lookup speed. And because of all these constraints, standard Linux operating systems and network stacks were really the performance bottleneck. So they were often used with minimal modification. Most software at that point in time was really written as a monolith because there wasn't really a concept of microservices or cloud architecture. And software would really only be run on bare metal configurations with limited options. It turns out that one of the most challenging feats in technology is building a reliable data warehouse, or really database in general. With the scope of features that need to be supported in data warehousing, creating a solution that's reliable that provides the correct answers is a daunting task, and in many cases takes years. Once a reliable code base is achieved over a long series of trials and customer implementations, companies usually upgrade that software to address any problems that come up, and that can take years to really get to a point where you reach stability. Once that happens, companies are really careful not to jeopardize that stability with any kind of massive changes. Up until recently, any code that was written for data warehouses was really written as a monolith. So in order to make any kind of real innovative changes to that software, you're kind of performing open heart surgery on a delicate patient. And this is why you see very often that many large companies and established data warehouses have a real problem with innovation. It tends to stagnate. Instead of really kind of innovating at a core level from the database perspective, they kind of build ecosystem solutions instead, which allow them to kind of connect over established interfaces. When cloud migrations kind of began at a large scale over the last few years, it kind of left traditional data warehousing companies and new cloud companies with a challenge. How do you move quickly to a new code base when it would take years. So most of those existing data warehousing companies ended up shoving those existing monoliths into containers to move them to the cloud. And it restricted what a lot of the cloud properties could do because they couldn't write their own. So many of those would go to kind of existing data warehousing companies and acquire them and then wrap those into their cloud software releases. But at the end of the day, these were just the same old code that was developed years ago, now repurposed for the cloud without any really foundational changes. Cloud migrations have been going full steam for years now, yet 80% of the data warehouse spend is still on premises. While the percentage of spend on data warehousing is changing, it's slow compared to the rest of the industry. So why is that? The huge data gravity associated with data warehousing makes cloud migrations difficult. And while housing data in the cloud is relatively cheap, the processing horsepower and networking requirements to support thousands of users against terabytes or even petabytes of data becomes very expensive and very challenging. One of the biggest challenges of moving data warehousing into the cloud is that the most credible solutions from cloud vendors not only fail to scale linearly to address the largest data challenges, and that's talking in the hundreds and terabytes up to petabytes, they don't offer a simple way to move back on premises if you run into a scaling challenge a month or even a year from now. So if you spend the time to migrate your data into a cloud data warehouse and you have to change your mind based on cost, and cost is very hard to predict in many of these cases, you'll have a real challenge on your hands. Getting the data back means you pay big money on fees to get your data back out of the cloud. And to mitigate this risk, you really have to maintain two code bases. One, which is your old EDW on premises, and then figure out the ETL to this new cloud solution and maintain them both, and ultimately multiple sets of interfaces and applications. Some cloud vendors offer a multi-cloud approach, but don't kind of account for the on-prem requirements at all. Furthermore, with new technologies like 5G, more and more data is being processed at the edge. As the number of network edge devices grow, so does the amount of data generated far away from centralized public clouds and even data centers. In some cases, the networks that reach out to the edge are limited in bandwidth, and the amount of data generated at the edge outstrips the ability to send it home. We're finding that more and more customers need a solution that can analyze data at the edge, allowing them to query it remotely. This would allow them to kind of refine the data out at the edge and only send home what's needed. But running solutions in a container, and I mean a real C container, not a Kubernetes container, has its limitations. Power, space, and cooling are at a premium. But most on-premises EDWs or traditional deployments can't handle multiple terabytes of data without taking up tons of floor space and too much power and too cooling to tackle this problem. But what if a data warehouse was so efficient it could easily process tens or even hundreds of terabytes of data at the edge with a minimal footprint? If you think about that kind of resource efficiency, it could also be applied to saving you money in the cloud by not using as many resources per query. That efficiency could also drive new levels of performance so that you could solve problems that you couldn't solve before. Yellowbrick's core architecture enables us to provide real-time analytics regardless of deployment model. We've created a new data warehouse designed for the latest software and hardware advancements. Our data warehouse is new down to its core foundation. We've shifted the way that core elements of computing interact. We've removed the largest bottlenecks from the CPU. We've removed capacity limitations for memory, and we've introduced a new level of processor efficiency. We have a completely new optimized data path, which I'll get into in the next few slides. And we've also created an adaptive kernel that adapts to its environment and utilizes different optimizations based on what's available. If you remember back to the assumptions we talked about at the beginning of the presentation, the most common type of storage when most data warehouses were written was hard drives. The only way to make hard drives perform is to put very large blocks on them to avoid head seeks. Once the data is stored in hard drives, you're able to read the data into the buffer cache in DRAM, and then the processor can utilize it. One of the things you'll notice is that the pipe between the hard drives and the actual pipe on the memory bus itself were drastically different. The performance of memory in these traditional architectures was much, much faster, and this is why you had to keep most of your data in the buffer cache to obtain any kind of performance. This worked okay for the period of time when these things were written. Now we fast forward into the future a bit, and we find that SSDs are actually very common. And now one of the things you'll notice is that the pipe between this primary storage and solid state disks and the pipe and the DRAM bus are about the same from a bandwidth perspective, not necessarily latency, but certainly bandwidth, which is what you care about in data warehousing. If your software was written for the old paradigm, this is what happens. You end up storing the data in those large blocks on the SSDs, which isn't necessarily advantageous for that flash media. Then the data is loaded into the buffer cache. And you'll notice now that we're streaming data at almost the same rate across both buses into that same buffer cache. And there's so much data now flowing into that buffer cache that there's contention when the processor needs to access memory to process data for something like an aggregate or a sort. Also, the streaming of data through the processor into memory throws out any kind of processor caches, which drastically decreases the efficiency of the processor itself. Yellowbrick addresses this problem by exploiting a new data path that wasn't available until recently, giving us a direct I/O path from NVMe storage to the processor without using main memory. We store the data in block sizes that are most advantageous to flash memory, helping in both performance and longevity of that flash. And something new to our Andromeda hardware is our FPGA accelerator called Kaleida. Kaleida assists in the compression and filtering of data. That means that the only data that's passed to the CPU has already been filtered and is pertinent to the query. It also means that the data has already been decompressed by the FPGA, thus offloading many CPU cycles. You'll notice now that we're loading data directly into the processor caches and not into a buffer cache. This is one of Yellowbrick's key advantages. There is no buffer cache or caching of data anywhere in the system. We've optimized the data path so there's no worry of hydrating caches to ensure a cache hit. All queries perform as if the data is in cache all the time. Another advantage of utilizing flash this way is the density. Flash memory is 10x more dense than DRAM, so we can keep data sets on a medium that's the same bandwidth as memory and 10 times the density. So at this point, if you would run a query, all data would have been processed from flash and not used main memory. We've reserved main memory for things like sorts and aggregates, and it also leaves a totally unfettered memory bus for optimal CPU performance and efficiency. This allows us to give you a system that requires less DRAM and, as I said before, requires no buffer cache. While the data path optimizations we just talked about are key, Yellowbrick innovations don't stop there and are pervasive throughout the solution. We've utilized software approaches from the fields of high-performance computing and high-frequency trading and implemented them to provide the most efficient data warehouse that's ever been built. We've innovated from the ground up, starting with memory management optimizations and custom threading model in the kernel. These reduce context switching and manage CPU caches to maintain their data until tasks are completed. We have custom device drivers for storage and network that offer massive reductions in the amount of code per I/O and increase networking efficiency by over 20x. And as I mentioned on the previous slide, the custom FPGA hardware accelerators that bring massive deterministic performance improvements that can't be obtained with the standard CPU approach. This means that Yellowbrick will run efficiently at the edge on smaller configurations and use less resources in the cloud to provide unrivaled performance on the largest data sets or on our hardware optimized instances. Some of our optimizations exploit capabilities in modern hardware like NVMe or InfiniBand networking by implementing custom drivers. If you look at different deployments, you'll have a wide variety of infrastructure with a wide variety of capabilities. Will it be a 5-year-old laptop, Amazon EKS, a Yellowbrick hardware optimized instance? Because of this wide variety, Yellowbrick software must make decisions about what is optimal in that configuration or what software should be used in each case. The 5-year-old laptop probably doesn't have NVMe or InfiniBand, whereas our hardware optimized instance does. Our software adapts to every environment to utilize the optimal configuration. The core improvements, like memory and thread management are consistent across these deployments. And to show you the efficiency, one of our engineers actually ran our Kubernetes-based deployment on a 5-year-old MacBook. Even with this very minimal hardware implementation, he was able to stream in a workload of 112,000 rows a second. Across all these deployments, you get the same consistent manageability, security, and unrivaled performance. Now I'm going to talk about our software architecture. One of the key things to think about is what do most customers want out of a data warehouse? They want complex queries against large data sets, and they want low latency inserts for streaming workloads. The problem is these two workloads are diametrically opposed from an architectural perspective. The scale-up row stores have historically been proven to handle those low latency commits for real-time inserts, while column-oriented stores have been more often used for their advantages with column separation and compression to optimize for large analytic queries. With Yellowbrick, data is actively managed in a hybrid row and column store that's been optimized for flash memory, as we talked about in the earlier discussion. That front-end row store minimizes the commit latency for real-time inserts, while the column store is designed to handle the massive analytic workloads, giving you the best of both worlds. Streaming inserts live in our row store temporarily and are automatically flushed to the back-end store based on time or volume without any kind of DBA interaction. The front-end row store is responsible for a bunch of functions, but in the interest of time, I just want to cover a couple more key points. And the first one is our Postgres connectivity. Our front end is based on Postgres because Postgres is one of the most widely used databases in the world and offers a compatible and common SQL dialect. This means that most analytic tools in the world already have a Postgres connector, which by the transitive property means Yellowbrick works with almost any analytic tool in the world. We also have our own custom tools like our bulk loader, which is capable of loading 20 million rows a second plus and moving data at line rate, which we also integrate with our partners into ETL tools to optimize for data movement. Also in our front end, you'll see that we have our query planner, query compiler, and they build parallel query plans that optimize the use of storage, network, and compute resources for all queries. The query plans are built with data locality in mind and minimize data movement across their network fabric. Another key point I'd like to cover is our workload management, which we'll get into more detail of in our advanced topics session. But our workload manager is a key feature because it allows DBAs to control resource allocation and as a result, quality of service for queries. Workload management divides the system up into resources or pools we often call lanes that are where kind of the queries are defined to run in. This means that no single query can dominate the system resources. DBAs can also define rules based on many factors, including users, applications, SQL, and define whether to prioritize or deprioritize queries. In addition, limits can be set for memory utilization or rows, so you don't have to worry about a new data scientist or analyst trying to return 1 billion rows to their desktop client. Kind of moving on to our back-end column store, Yellowbrick is an MPP database, which offers linear scalability on that back-end column store. Our column store has all the optimizations that we discussed earlier in the presentation around memory and thread management on the YBOS kernel. And our storage engine is a scale-out service that implements the distributed column store. And this is where that flash-optimized file system and erasure encoding scheme live. This is not only offers kind of peak efficiency, but also ensures maximum availability. Our storage engine ensures that even if multiple nodes in the cluster are lost, the system's still available. Our execution engine lives on top of that storage engine and is also a scale-out service that executes SQL query plans. And they run the SQL compiled code from the query compiler in a massively parallel function. Unlike many monolithic data warehousing software stacks of yesteryear, Yellowbrick's architecture is comprised of services that can be scaled out and adapted to meet the needs of the largest challenges and deployed in almost any environment. So what does all this architecture and innovation really mean? I wanted to show you what our value looks like to some of our customers, and this is just a small subset of them. It's not enough to perform well. You have to be consistent. You have to be reliable over time. You have to work well in a technology ecosystem and adapt to changing demands. Some of our customers have the most demanding workloads in their industries, and this is the business value of Yellowbrick, not only processing queries in record times, but the translation of that agility into solving problems that couldn't be solved before. Now that you have an idea about our architecture and the benefits of Yellowbrick, let's talk about deployments. Remember the earlier discussion where we laid out the challenges of moving into the cloud and the potential pitfalls of being locked in, as well as the challenges of trying to process data at the edge with minimal resources. Yellowbrick is now offering total flexibility and freedom. In private clouds, we can provide our own hardware-optimized instances on Andromeda that have unrivaled performance and density, offering over 6 petabytes of flash-based storage, as well as 2,500 physical cores and about a half rack of gear that can support almost any data warehouse workload imaginable. If you already have your own private cloud up and running, we have you covered with our cloud-native Kubernetes-based solution that offers all the same features and functions on your own private cloud hardware stack. In the public cloud, we offer a fully managed service based on our optimized instances, and this is a fully managed solution you can access via private link that offers flexible services around backups as well as replication for disaster recovery. These are dedicated Andromeda-based instances that offer the highest performance available in the public cloud today. And if you'd rather manage it yourself in your own VPC, we offer our cloud-native solution, just like in our private cloud, to be run on cloud Kubernetes stacks like EKS. At the edge, Yellowbrick's unrivaled efficiency really shines. And we've had customers request to run Yellowbrick on things like laptops, 1U servers, and other specialized hardware. We can also offer Andromeda 3-node configurations supporting up to 145 terabytes of structured data with minimal power and cooling requirements. And to make distributed cloud a reality, we've announced the Yellowbrick Manager that provides a single pane of glass to manage instances across the spectrum from edge to public clouds to in your data center, all from a single pane of glass. When talking to customers, most are comfortable with application migrations to the cloud, but one of the larger challenges is the migration of the data itself. Yellowbrick can create a common data layer across all deployments using our built-in replication solution. Replication is included in all Yellowbrick deployments and can be easily configured within a few seconds just using a few commands. Replication is per database and allows you to replicate data where it's needed for DR or locality purposes. Replicated data is compressed and frequency of replication is flexible to allow our replication to operate within a wide range of network speeds and latencies. The best part for our customers is that unlike most other vendors, Yellowbrick doesn't charge extra for replication and doesn't require any additional licensing or software. So if you have Yellowbrick, you have replication, configure it, use it as much as you like. And lastly, let's touch on security. When implementing a data warehousing solution across public, private clouds, and at the edge, you want to ensure that you have a consistent security posture across all deployment. Yellowbrick offers layered and pervasive security controls throughout the stack. Our hardware-optimized instances offer AES-256 self-encrypting drives for encryption at rest. And in our cloud-native deployments, we offer that same AES-256, but it's based on software and at the column level. All encryption keys are managed by our key vault, and we provide role-based access control with fine-grained object grants. We integrate easily with LDAP, Active Directory, and OAuth, and all external connections are encrypted with SSL TLS, whether it's our web-based interfaces, ODBC, or our own custom toolsets. Yellowbrick has designed the optimal solution for distributed clouds. Our unparalleled resource efficiency allows our customers to solve problems that were previously impossible to solve. It allows for real-time analytics at the edge where resources are limited, and our uniform infrastructure, unified control plane, and pervasive security allow you to deploy solutions where they're needed